Okay, everybody, we're going to get underway. So tonight we're going to look at ideas within Chapter 6. We got a little head start on that last time, and I'm confident we'll get a big chunk of it done this evening, and we can wrap it up on Thursday. So I think we'll be in good shape heading in towards the second exam. So a couple things here to begin with logistically. I mentioned last time how we're going to be reaching out to some students in the class here to see if they can participate in some interviews as part of a research project. To give you an update on that, that's in progress. I've got my my students contacting people within the class here. So I'd say we're setting up group interviews, and we're going to try to get through as many of the students within this class as we can. So if you're not contacted right away, you're somewhere in line. We're going to see how many we can get through, but I really appreciate the initial strong response. Looking ahead to the exam, taking care of a few logistics and sort of making a plan going forward. But it's very important to know the date and time. So we see listed on the syllabus, the exam's Monday, March 8th. The coverage on that is going to be chapters 4, 5, and 6. It uses ideas from earlier in the course, but nothing that is like sneaks in on you. Okay, when I say earlier, well, we keep doing things with naming polyatomic anions, for example. So those kind of topics and skills still persist. The makeup exam, if you know that you have a conflict, if you're not sure if you can take the makeup or not, if you recall, if you look on the syllabus for that, there's a link for the makeup exam policy, and that's where you can request that. As far as getting ready for the test, bringing together ideas, got a couple resources to point out to you. First is the review that I've posted in Perusal. So within there, I've listed that for this evening due at midnight, and I'm going to be providing extra credit within the Perusal program for that. I had to put it somewhere. I don't know if Tuesday is the best time slot within that. So my plan is, I think it's valuable. I'm enjoying the comments that you're making. I think they're beneficial. So I'm going to end up moving that back or forward. I'm going to move it ahead to Thursday of this week. I had to have it as a placeholder within that one, and I don't want you having to race to finish it this evening. So I'm going to be shifting the deadline on that. So if you haven't gotten to it yet, it's something that I think might be beneficial for you. Another thing that's beneficial are the practice tests that are in Carmen. you're going to get credit for attempting those. It's not something that counts as a score where if you don't do great on them, it's some kind of negative. I want to be able to give you some credit for attempting them. If you look within Carmen on that, there's the different modules in the course, and there's one called practice exams. If you click on that one, you'll see that there's information here leading up to midterm 2. I was looking through the details on this, and I think it's really well done. My colleagues have put that together, and I think it's really strong. So this was in the module called practice exams. If you look for preparation for midterm 2, if you click on that, it shows you the provided information. If it's constants, activity series, solubility guidelines, and it even gives you then a worked out solution key and sort of a strategy for going forward from that. So for each of those, they're set up as quizzes within Carmen. And so this will also allow you to practice the system and see how it works. After tonight's class, we won't have all of the ideas in chapter 4, 5, and 6, but we'll have quite a few. So I think this could be a really good resource as we begin moving ahead towards the next exam. So I'm curious within here, let me shoot you a quick poll. Which of these resources do you think you're going to use? The review and perusal, and then there's 3 different practice tests. Which of these, select all that apply for you, please. As those come in, there was a question within the chat as far as will there be a review of ideas for chapter 6? What I'm probably going to do is I'm going to look to see what I can take away from the initial performance in the practice test within the first one, and see what kind of information there I should return to, or I should supplement a little bit. And I can probably either pick that up in class on Thursday or make some other kind of supporting video for that. So I'm gonna, as far as stuff from chapter 6, I mean, we're really just exploring the ideas now. And if it seems like there's some way that we need to sort of supplement that, I can try to do so. So as I look within the distribution here, share with you all, pretty strong consensus within here, especially in terms of attempting to take the first practice test. I think these are all great resources. So let's see how it goes as far as putting it together. I think it's going to be time well spent for you. Looking then as far as ideas within chapter 6 that we had last time, I'm going to review just a couple of those here. So in last class, we were able to work a little bit on 6.1 through 6.3. So I want to try to make clear what are the main things that we're going to want to be able to do with these ideas. So for that first one, looking at properties of light, which is also called electromagnetic radiation, we saw that we had the different regions of the electromagnetic spectrum. You don't need to know specific values, but you need to be able to put them in order. The ones that I see on the far left-hand side, gamma rays, X-rays, involve high frequency, short wavelength, and high energy. And then the ones way on the right-hand side, you see are just the opposite for each of those terms. We also had calculations involving the speed of light and how that had a relationship with the wavelength and the frequency, lambda nu. So the speed of light would be a constant that would be given for you, but we saw that quite frequently we have to do conversions involving going from frequency to wavelength or back the other way. When I look at this one, the part of this that I know gives students the most trouble is just this relationship right here. Because if something has a short wavelength, that means that it has a high frequency and therefore a high energy. And if it has a very long wavelength, that's a low energy. And I know why this is confusing, because usually when something's big, that means it's bigger. And in this case, it's not the case. It is the short wavelength that corresponds to the higher energy. So if you can internalize that, I think it'll help you read the different questions that we come across. This is the kind of question as far as the format that I typically see on exams. So here I see different regions of the electromagnetic spectrum, different relationships involving energy, frequency, wavelength, and to see which ones were therefore true. This would be a question that comes back to the objective of knowing the different regions of the electromagnetic spectrum and being able to put them in order based on energy, frequency, and wavelength. We looked in 6.2 at the idea of energy being quantized, having specific values, specific values as in a staircase has specific values, a particular, unlike a ramp, which would be continuous. So this was being proposed here by Planck with his investigation of black body radiation. And it was explained using this expression E equals h nu, which was talking about then the smallest amount of energy that would be possible. Now, we don't do a lot with Planck's description, but we do take that expression E equals h nu, and it's connected then with Einstein's explanation for the photoelectric effect. So within this one, the phenomenon's a little bit, there's a little bit more to it. As far as the phenomena, we saw that within this experiment, light could be shined onto a surface of a metal, which could cause electrons to be ejected. And that the frequency of the light was what was crucial. It must be above a particular threshold value. If it was below that value, it didn't matter how bright the light was, no electrons were being ejected. This is Einstein using the expression E equals h nu to talk about the energy of the light in terms of its frequency. His explanation for this was that the light was acting like particles, which are called photons, and each photon had this energy E equals h nu. And this was unusual because there's other experiments that would support the idea that light acts like a wave. And Einstein in this one's describing how it acts as a particle. I grabbed this, the same PhET sim here to sort of illustrate these features once again. So let's start directing the light at the metal surface. It's getting brighter, and I see electrons being ejected from the metal surface. If I make it all the way dim, all the way off, it stops being ejected. So I'm going to switch it now and make it so the brightness corresponds to photons being directed at the surface. As the intensity goes up, that means more photons are striking the metal surface. If we change the wavelength here, I'm making the wavelength longer, which means it's going to lower in energy. It's going green, it's going towards the red. Eventually I reach such a low energy that even though it's quite bright, even though a lot of photons are being directed at the surface, they did not have sufficient energy to remove the electrons. Once we return and we exceed the work function of the metal, they're being ejected once again. I'm trying to show the relationship between how many photons are striking the surface and the energy that they have with this expression E equals h nu. This was for sodium metal surface. If we change it to something like platinum, the energy is now too small. In order to increase the energy of the light, changing the intensity, the brightness isn't going to do anything, but we can change the wavelength. We can make it so it's now reaching into the ultraviolet, and eventually we're going to reach a high enough energy so now they can be ejected. As I look at these different features here for what's going on, in terms of a photoelectric effect, I think we had a description of the light, its energy, which we could think of in terms of either the wavelength or the frequency, because we can convert back between those. So in this experiment, we had the light, we had the energy of the light, and we also had its intensity, which was its brightness. These were different things. Energy was related to E equals h nu. The intensity of the light was the number of photons. And we also then had the metal that it was striking. All of these are fitting together. The one that's going to be that we manipulate or we understand the most, I would say, is the energy, with our two expressions E equals h nu and C equals lambda nu. I'd say these other ones, the intensity of the source or the work function of the metal, that's not something we're going to calculate. We're going to do calculations involving the energy, but it's good to know how the three different parts fit together. Here's some end of chapter problems that I saw that are looking at you going back and forth between this expression E equals h nu and C equals lambda nu. So those are some suggested problems on that part of it. Moving on within that one, we're up to 6.3, line spectrums, Bohr's model of the hydrogen atom. So we saw last time, if you take white light, that includes photons of all different energies. When it's passed through a prism, you see the full spectrum, Roy G. Biv, all the colors. A line spectrum, though, is something that doesn't have every color. If you were to take something like hydrogen atoms, put it into a electric tube, send electricity through it. When you have that light now go through a prism, it separates it out into its component colors, its component photons. And for something like hydrogen, you don't see every, sorry about that, you don't see every color there. You see some distinct lines. So the question was, well, why does an atom like this hydrogen atom absorb or emit only certain characteristic photons? What does that behavior tell us about the electronic structure of the atom? And when I say electronic structure, that's the title here of chapter 6. That is saying, tell me about the electrons in the atom, not really about the protons and neutrons. The electronic structure is thinking about where are the electrons found and what is the energy. That's what chapter 6 is about. So within Bohr's model, and this is where we were leaving off last time, we saw that he had 3 different characteristics to his model, 3 different features that he was aware of that he was bringing together. There was the nuclear model of the atom, which Rutherford had proposed based on a gold foil experiment, this line spectrum for the emission of hydrogen, and the idea of quantized energy equals h nu that Einstein has used to explain the photoelectric effect. So let's see how this comes together. These different parts come together for what Bohr is proposing the hydrogen atom is like. So first of all, this idea of the gold foil experiment and a nucleus. So in his model, he's going to say that you have a nucleus and that's where the protons or neutrons would be found. So he has that in the center of his atom. And the electrons he has are outside of that nucleus. He's placing the electrons in these circular orbits, these rings that are around the nucleus. So in his model, the electron can only be on particular rings. Now, this idea of quantized energy, where does this fit in? When the electron is on a particular ring in a particular orbit, our system there, the hydrogen atom, has a particular energy to it. Notice how it can have an energy value of n equals 1, 2, 3, 4. When I look at those particular values, I am seeing that the distance here is quantized. It can only have certain distances away from the nucleus. And the energy levels are quantized. They can only have certain specific values. So in Bohr's model, we see that both the energy and the position of the electron, they're quantized. They have specific values to them. This lowest one is called the ground state. So that's a term that we're going to keep using in our other models. The lowest energy configuration for the electrons is called the ground state. And that is occurring in his model when n equals 1. N is his quantum number. So you see that he has the quantum number n that can correspond to energy levels 1, 2, 3, 4, 5, 6, etc. Now with the hydrogen atom, notice how the energy levels are getting closer and closer together as n increases. There's a big difference between 1 and 2. And then it starts to get closer and closer together as you go higher up. That's another feature that we're going to make use of. Now the last part of it, how does this fit together then with the line spectrum? This would be an expression describing where the lines are found. And the way that's fitting then with Bohr's model is this. Let's say a photon comes in and moves the electron when it absorbs energy from n equals 1 to, let's say, n equals 5. That's what these n sub values mean. It's initially at level 1, it interacts with the photon, and it goes up to level 5. I'm saying photons being absorbed. It's being added to the hydrogen atom, and it's moving the electron up to an excited state. Now, let's say if it now finds its way back down from there, it's going to eventually return back down to the ground state. So let's say it starts going down, it goes from 5 to 3. It's initially at 5 and it goes down to 3. That would cause a photon to be emitted. Energy would be released. And that's what this line spectrum is recording. It's recording the energy of the emitted photons as they're coming back down. And notice they have these integer values, n values. That's what was also showing up in this expression here. I know we've got a lot of different representations. We have what the atom is like, the energy levels, and then what you could observe in the line spectrum. Let me play for you here this aspect of the PhET sim and see if we can make sense of this. The features within this that we're going to use going forward, the Bohr model is not our final model, but we are going to retain the idea that the electrons exist in these discrete energy levels, which are described by quantum numbers. So as we look at the simulation, let's look for that. And also how energy is involved in the transition from one energy level to another. So here we have the electron in that innermost level. And here would be the energy that corresponds to it. I'm going to start sending photons through it. When the photons interact with that electron, it moves it to a higher energy level. It moves it further away from the nucleus. So if I look at this region here in the center, I see the electron moving in rings, and sometimes it moves further out, and then it moves back in to a ring closer to the center. And as it's going back and forth with there, it's moving to different energy levels. When it's at n equals 1, it's closest to the nucleus. And they're even showing here arrows as far as, is it going further away from the nucleus or back closer towards it? I'm speeding it up here so that we can see as time goes on, we're beginning to collect the line spectrum here for hydrogen. This is Bohr's model of how he's trying to describe the electronic structure, where the electron is found in the atom, and connect it to something that was experimentally observed in the lab, the emission spectrum here. So let's think now, how are we going to begin to use this information? What are we going to be asked to do with it? So here's a couple of different things I grabbed from the book. A couple of different figures and sets of equations. So what do we want to take away from that? Let's take away this idea right here initially, that when a photon is absorbed by the electron, it moves from a lower to a higher energy level. And that when it then goes back in the other direction from a higher to a lower, it's going to emit a photon. So a photon is a unit of energy. It takes energy to move it from a lower to a higher energy level. And energy is released when it goes from a higher to a lower one. So let's be able to make sense of arrows like that and think about what that means for the n values. Second, let's have this idea of the spatial arrangement for these energy levels, how there's a really large gap between 1 and 2. And then it starts to get smaller between 2 and 3, and even smaller yet between 3 and 4 and 3 and 5. These expressions here at the bottom, we're not going to really be doing calculations with those, okay? Those calculations are going to describe sort of this pattern that I see here. But I think if we can interpret the figures and understand the figures, that's more of where we're going to want to be. So if I look at typical questions, here's an end of chapter question. So notice within here, I'll give you a second to read it through. So this question is saying, consider this to be then the energy levels that we have for the hydrogen atom. And it's showing different possible transitions where an electron could go from levels 4 to 3, 3 to 2, or 2 to 1. And we're asked to match that up with these electromagnetic waves. So the first thing I'm going to do is I'm going to look and say, okay, this first one right here, this looks like it's got a very short wavelength, which means a very high frequency. This would be very high in energy. And if I look at number 3, this looks like a very long wavelength. And so this would be the lowest in energy. So if I try to connect these, then this question is asking us to bring together different ideas. I'd say this one on the left is describing something that has a high frequency and a short wavelength. That would be the highest energy photon when I think about E equals h nu. This would lead to the one that corresponds to the largest energy difference. And that's between levels 2 and 1. And I could use the same kind of reasoning here to say this one right here, this is the longest wavelength. That would be the smallest in energy. So that would be the smallest energy transition. And that would be the one between 4 and 3. So I'm not doing any math there, but I'm qualitatively describing what's going on. A really typical way that I've seen it asked on exams is this format right here. So this is the similar end of chapter question 46. Which of these electronic transitions for a hydrogen atom corresponds to the emission of a photon with the shortest wavelength. This is one, you're not being asked to do any math, but you're asked to qualitatively know how are the energy levels arranged for hydrogen. Let me send you this one here, the polling question. Give this one a try. Take about 10 more seconds. Okay, so here's our results. Most frequent answer here, about half the class is choosing choice D on this. Let me talk this through and explain my reasoning. So within this one, it says it's the hydrogen atom. So before I do anything else, I know the relative spacing in the hydrogen atom. I know that they're going to get closer and closer together as the N value gets bigger. Second thing I'm going to do is I'm going to read carefully because it's talking about the emission of a photon. Sometimes these questions are set up where it talks about absorbing it. Sometimes it talks about emitting it. In order to emit it, I know that I need to be going from a higher energy level to a lower one. So if I look at my choices right there of going from higher energy to lower, I see two different choices. C and D are both examples. Initially at 4, going down to 2, if I'm initial and final, that would involve emission of a photon. If the electron goes from 3 to 1, emission of a photon. So I think our choice is based on emission, it has to be C or D. And then the last feature, it says the shortest wavelength. I'm thinking to myself, okay, short wavelength means higher in energy. There's a larger gap between 3 and 1 than there is between 4 and 2. And that's because of how the energy levels converge. So in order to ask this one, the setup within this, I have to look for a couple different features. First of all, it's specifying for certain that this is a hydrogen atom because this pattern of how they get closer and closer together, that's only true for hydrogen. So this is looking at our model for the hydrogen atom, our simplest atom. It's only going to be asked for hydrogen atom if it's one where you're supposed to know that they converge. The second feature is I'm going to read it very carefully and consider, is it being absorbed or emitted? And then the third feature, whether it might be in terms of energy, it might be in terms of wavelength, it might be in terms of frequency. I've got to be able to think of that last term there as well. Very typical exam question. Wouldn't be surprised to see something like this on your test. Here's some that we had end of chapter that are on that same subject. So within this one for 6.38, it's first of all just asking, does this involve energy being emitted or absorbed with different things taking place? Changing N values or changing position. And then the second one right here, this is closer to the one of, can you do a ranking? Can you talk about the relative energy differences within that? Let me add one more feature that might help you make sense of this last one right here. So here I showed the different transitions again with hydrogen. And we see a really big gap between 1 and 2, 1 and 3, 1 and 4, anything here with N equals 1. It turns out any of those involve photons that are in the ultraviolet. Anything involving N equals 1 involves a photon in the ultraviolet. This next set right here, anything involving N equals 2, and by that I mean 3 to 2, 4 to 2, 5 to 2, those are all in the visible region. Take a second. What do you think they are if they're involving n equals 3? We had the ultraviolet, we had the visible. Those are all involving the infrared. So that might help you a little bit when you're doing these kinds of particular ordering as well. It doesn't have to be that way, you know. I mean, nature doesn't have to say principal quantum number 2 means this, but that, I mean, because when we're talking about visible light, after all, that's just how our eyes work, right? You could be a different animal and see different regions of the electromagnetic spectrum. We might have animals right now listening to this. I see my dog over here somewhat listening. I think his vision of the electromagnetic spectrum is different than mine. I'm getting too far afield, but I'm looking at him sitting on this futon over here, and I'm trying to connect him to the Bohr atom somehow. Okay, this idea right here of Bohr having a model is sort of a transition one. It's an important transition one, but it leaves a few questions unanswered. It could explain the emission spectrum for hydrogen, but not for other elements. It only works for hydrogen. And he doesn't tell us things like, well, why would the ground state be stable? Why can it only go down to n equals 1? Why would it be found at these quantized values, but never somehow in between? And in a way, if a photon comes in and moves it from, let's say, n equals 1 to n equals 2, how does it know it has the right amount of energy to go from n equals 1 to n equals 2? How does it make the trip? Only if it has the right amount of energy. So what he's doing right here is he's taking some like classical physics ideas. He's added in some aspects of energy being quantized. But what we're going to find is that the world in this realm is actually stranger than what Bohr was proposing. So if we took these same features right here, this was summarizing Bohr's picture. We had a description for what his atom looked like. We had quantized energy levels, and it gave us the correct emission spectrum. So it must have some features that would be right there too. Now I'm going to change this. Instead of calling it Bohr's model, I'm going to change the name. And by changing the name, I'm keeping a lot of it the same. I'm keeping the energy levels the same. I'm keeping the emission spectrum the same, but I've changed this picture of the atom right here. Okay, so this one right here, this is from a physicist called Louis de Broglie. He's a French nobleman at the time, and he comes up with a very different picture for what he thinks the atom is like. So first of all, if you look at his name right here, French nobleman, Louis de Broglie. It rhymes with destroy. It doesn't look like it would be spelled de Broglie, but that's how I pronounce de Broglie, but that's how it is. And the reason I'm bringing that up is you will probably see this name again, perhaps in a physics class, perhaps in some other science class. And I guarantee you they are going to mispronounce his name. You will hear it pronounced de Broglie, de Broglie. They try to make it sound French or something. Everybody gets it wrong. You will not get it wrong, okay? If I could have that be somehow a voice part of your next test, I would. It's pronounced Louis de Broglie. So what I want you to do is if someone mispronounces it, I want you to raise your hand. You'll probably be in an in-person class at that time. Say, au contraire, Louis de Broglie is the correct way to pronounce it, okay? Feel empowered with that information. Now, moving back to the chemistry side, this is what he's done different. Instead of saying that the electron is a particle that's moving along in an orbit, he switches that and he says, what if it is a wave instead? Because what we've seen is that light has behaviors of a wave, and Einstein turned that around and said, well, it seems like it also has characteristics of a particle. Louis de Broglie looks at it from the other side and says, well, what if things that we think are particles have characteristics of waves? What would be their wavelength? So he turns it around from the other direction. It's a crazy idea, but it turns out he's right. What would be the wavelength that matter would have? Here's his expression for what the wavelength of matter has. In the numerator is Planck's constant. In the denominator is its momentum, its mass times its velocity. This can be used to calculate the wavelength that matter has. It's usually too small to be measured, but it becomes important when we're looking at things like electrons. Let me show you when I say becomes important. So we're going to briefly look at this idea in 6.4, how matter can have descriptions of a wave as well. So when did this become important? And how does it give rise to uncertainty in our measurements? Let's just briefly look at this idea. And when I say briefly, I wouldn't expect this to be a major focus of your test. So first of all, here's a picture of Louis de Broglie. Does he look like a French nobleman? Yes, he does. Okay, so here he is. So let's calculate what would be the wavelength if we have an electron that has a particular velocity and a particular mass. So in order to do these calculations, it's Planck's constant over the momentum, the mass and the velocity. Well, in order to get joules, which is Planck's constant, into these other terms, we have to write a fuller expression for what a joule is. So a joule is defined as a kilogram meter squared per second squared. If we do that, it allows us to cancel our various terms. Again, I don't think you're going to have to do math within this one. I mean, we can qualitatively understand the expression, but this is how the math works out in the calculation. This is introducing a new unit for us, which is called an angstrom. So if you see this capital A with a 0 above it, that's called an angstrom. An angstrom is 10 to the minus 10th meters. Really small, but it's on the scale of our atom. So the wavelength of the electron, it's on the same scale as the atom. And that is something we could actually measure. 10 to the minus 10th meters, that's similar to X-rays. So we can actually measure the wavelength that an electron would have. Now, let's say we looked at an everyday object. So I need an example of an everyday object. So I like this one that I grabbed on the internet because it was a cricket ball. I've never played cricket, but I thought I always see these and set them up with like baseballs or golf balls. But this one's a cricket ball, massive, about 100 grams, and you could throw it about 100 kilometers per hour. If you set up exactly the same expression, notice how this one has a much smaller wavelength. This cricket ball, when you throw it, so a cricket ball is like a baseball. When you throw it right there, it has a ridiculously small wavelength. Would it still have a wavelength? Yes, but it's way too small for us to ever measure. That's how we say that everyday objects, even if they have a wavelength, we can't measure them. Within this one, we just saw that that wavelength was 10 to the minus 36. Our whole electromagnetic spectrum only goes down to about 10 to the minus 11th. 10 to the minus 36, no way we could possibly measure that. That's what it means to say on what scale are these wavelengths important or not. Now, another aspect of this, which is discussed here in 6.4, is the idea of the uncertainty principle. In classical physics, and by classical physics, I mean physics from Isaac Newton all the way about 1900, you could at least in theory describe every characteristic of a particle. And by every characteristic, I mean, if you had a supercomputer that could look at all of the data, let's say if you had a pool table. And by all the data, I mean, let's say you struck a ball and you could measure the initial velocity, the angle with which it was being struck, the friction of the table, the air resistance, what happened when it struck the wall, what happened when it struck another ball. At least in theory, you could put all of that into a supercomputer, and after one shot, it would tell you, boom, where every single ball is going to end up. That's what it means to say it is deterministic. At least in theory, we can know absolutely everything about the system. However, we're going to see that in our quantum world, that's no longer the case. In our expression here from the Heisenberg uncertainty principle, this is saying, and this is another one, let's know the idea, but not the math. It's saying that the uncertainty that you have when you measure the position of something and the uncertainty you have when you measure its momentum, the product of those has to be larger than this quantity involving Planck's constant. It must be above a particular threshold value. You cannot know both of these completely. The more certain you are with one of them, the less certain you are of being able to measure the other one at the same time. It's not that we're not being smart enough. we don't have a clever enough experiment. He is saying in this realm, there's a fundamental limitation for how precisely we can know two measured values, such as the position and the momentum. This is going to then inform the models that we're going to have for the hydrogen atom. And by that, I mean, if we think back within our Bohr's model here, Bohr's model is before Heisenberg's. Heisenberg comes and works with him actually in Copenhagen shortly after he's proposed this. So within this one right here, it violates the uncertainty principle. Because notice what we have. Bohr knows precisely where the electron is being found on a particular ring. And at that time, he knows its exact energy value too. He knows both of these features. And we just said, according to this, you can't know both of the features precisely. Our next model, and the one that we currently use, the Schrodinger's model, it gets around this. It doesn't make the claim that you can know both the position and the momentum and the energy at the same time with complete precision. He is going to again say that the energy values are quantized. The energy values in the atom are going to be precisely known. So instead of then looking at the electron on rings of some kind, we're going to talk about it in terms of the probability of finding it in a particular region of space. So we're going to know the energy very precisely. In the position, we're going to say, well, it's usually in this type of area. We're going to have to describe it in terms of probabilities instead. And that's what we're going to then take up with our last model here. And by last model, this is the one we currently use in chemistry. The Schrodinger model, which is our quantum mechanical model. So within here, this first one, compare and contrast the atomic orbitals that we have in Schrodinger's model with those used in Bohr. Well, in Bohr's model, they were just these rings. We described them by a particular quantum number. N equals 1, 2, 3, 4. We're going to see within Schrodinger's model, these atomic orbitals become more complex. And we're going to need to use quantum numbers beyond just the n value to describe them. Here's a picture of Schrodinger. So he's an Austrian physicist. All of these people are doing their work in the early 20s. Here's an expression for what's called the wave equation. You're not going to do any math with this, but what he's doing within this is, just like de Broglie, he's recognizing that we need to have both a wave-like characteristic and a particle-like characteristic for our electron. Both of those features end up showing up in this. Within the book here, we're going to qualitatively look at some of the results, and we're going to use that for the hydrogen atom. So this is a picture I grabbed from that PhET sim describing then the Schrodinger model. I see that we have energy levels once again. We have an emission spectrum, but what the atom is looking like, it's not defined the same way. The position of the electron, it's like somehow related to these clouds somehow. The energy levels, I still have n equals 1, 2, 3, but notice they're spread out. Instead of just having one line, I have more than one line there. This particular one, it's going to work great. The experimental result is the emission spectrum, and it does a great job with the emission spectrum. But you also see, once again, my point of how this is consistent then with the Heisenberg uncertainty principle in the way that Bohr's is not. It's only going to precisely know one of these features at a particular point in time. The energy will be precisely known, so we're going to describe the position based on probability. So if we look a little bit more closely here, these clouds, we still have our nucleus here in the center, but the electron is found in this more ill-defined region around it. Those are called atomic orbitals. In Bohr, it was a little bit more rigid, like an orbit, like a planet. They kept the same kind of name, but they call it an orbital to say that it's not as well defined. It's describing the probability of finding the electron in a particular region. Now, the orbitals that we have here will once again use quantum numbers. Bohr had the quantum number n. We're going to see that we need more quantum numbers than just n. We're going to need quantum numbers that are going to describe not just the energy, but also aspects of like its shape. Now, I know within a pre-class video, I shared some ideas about quantum numbers, and I really like this question, this comment from someone at the end. They said they had trouble understanding the information in the video, and they weren't really equipped to ask good questions or have good comments, because they really were not sure, well, what was the purpose of these quantum numbers? I thought that was an outstanding observation. They'd given it a try, but they weren't really seeing what the point was. So the idea, the purpose of quantum numbers, let me try it this way. So here's my picture here. I'm trying to show a Bohr model. So I've got a nucleus in the center. And within our Bohr picture, if you tell me the n value, n equals 1, 2, 3, 4, I can tell you precisely the ring that that electron is found in. In the Bohr model, I only need one quantum number to tell you where the electron is found. But let's say we change a little bit. Let's say we had this ring here, and let's say I make a model of the atom where it has a ring and then it has another ring perpendicular to it. So it can either be pointed up and down in one plane or front and back in the other. So let's say this is my model of what the hydrogen atom looks like. If my model has two rings like this, I don't think I could just use one quantum number, because I need to tell you what ring is it on. I could have n equals 1 to show how far it is away from the nucleus, but maybe I need another one to say, is it on the ring going up and down, or is it on the ring going front to back? Notice as my description for where the electron is found gets more complex, I can't just have one quantum number. Or let's say this was your model. Let's say you said the electron could be in a circle, or it could be in an ellipse. It could be an ellipse with a different geometry around it. In an ellipse, you have two different factors describing what's going on. If A and B are both exactly the same, you have a circle. If A gets bigger and bigger, then it gets elongated out. This idea of saying, well, maybe they're not rings, maybe they're ellipses. If you do that, you need more quantum numbers. And in fact, that idea right there, the reason I bring that one up, that's exactly what Bohr did next. Bohr's approach only worked for the hydrogen atom. So the way that he began to change it, say, oh, well, maybe it's a little bit more complex in a different way. He started elongating it. He started turning them into ellipses. And in order to do that, you need more quantum numbers. So I'm not saying that we're using ellipses, but what is the purpose of quantum numbers? We're describing more complex orbitals. And in order to describe these more complex ones, we're going to need more than just a single quantum number. We're going to need the quantum numbers that I show here in this table. So at the top right here, this is the an expression for the Schrodinger equation. The reason I'm showing the whole expression here is within that, in that generalized function, you see the different quantum numbers. I see an n value, I see an L value, I see an m sub L value. These are showing up in the whole big expression. When these have particular values, they describe particular types of orbitals. There's one that doesn't show up in this that gets added on later on, which we'll talk about next time, which is the magnetic spin quantum number, m sub s. So what do we do with this? We're not going to do math using the Schrodinger equation. What we need to do is we need to understand what each of these quantum numbers is telling us and how they fit together to give us certain allowed values for where the electrons may be found. So as far as, first of all, what are they telling us? The n value, the principal quantum number, is telling us something about the size of the orbital. The L value is telling us about its shape. M sub L value tells us how that particular orbital is oriented, aligned in space. And we'll see that the last one, M sub S, tells us about the spin that that particular electron has. Now, when I say that there's allowed, there's particular relationships for how these quantum numbers fit together. You can't just make them up and say, well, I'm going to say this one has a value of, I don't know, 1 3/4. There's only certain allowed values that they can have, and they also fit together in certain ways. Our principal quantum number starts at 1 and goes up from there, 1, 2, 3, 4, 5. The L value is related to the n value. It starts at 0 and goes all the way up to n minus 1. So that's what I'm saying. There's relationships amongst these. In the Bohr model, we only had a single quantum number, but now the atomic orbitals we're looking at are more complex. So we need more information to describe them. So here I show a figure that we can use to describe the energy levels in the hydrogen atom. So right now, this looks really similar to our Bohr picture. N equals 1, N equals 2, N equals 3, all the way up to N equals infinity. Let's start now supplementing this and thinking about the different quantum numbers and how they fit together. So each box within this diagram corresponds to an atomic orbital where the electron could be found. N equals 1, way at the bottom here is the ground state. Now what I've added to that, I've put them into columns deliberately, where this first column here corresponds to L equals 0. The second L equals 1, and then L equals 2. Those particular L values, those are given names. If you've heard of something called a 1s orbital, a 3s orbital, a 2p orbital, those designations correspond to what these L values were. When L equals 1, it's called an s orbital. L equals 0 is called an s. L equals 1 is a p, d, and f. By the time we get through that, we've covered all the orbitals we need for the periodic table. So within this first column right here, we could see if this is L equals 0, we have a 1s orbital, a 2s orbital, and a 3s orbital. This would correspond to a 2p and a 3p, and then a 3d. Each of those, that designation, SP or D, is going along with what the L value is. Now, why am I writing one box here for the S, 3 boxes for the P, 5 boxes for the D? What am I trying to designate there? That's what the M sub L values are. M sub L values go all the way from negative L to positive L, and the values in between. So when L equals 0, M sub L must equal 0. When L equals 1, then they go all the way from positive 1 to negative 1. When L equals 2, they go all the way from positive 2 to negative 2. 2, 1, 0, negative 1, negative 2, that gives me the 5 options right there. This picture that I'm drawing right here, I like it because it really summarizes, for me, the relationship amongst the allowed quantum numbers. And as I'm thinking within this one, I mean, you know how your test format is. Your test format is one where you can have supporting resources. If it's me, I probably have a sketch like this, because this does a really good job, I think, of summarizing the allowed quantum numbers. That last one, the spin, that's not something we really need right now when we only have 1 electron. But that's what our last quantum number is. The rule on that one, in a way, it doesn't fit with the other ones. It's simply going to have a value of either plus 1/2 or minus 1/2. So it's not tied into these other ones. The M sub S value is simply going to be either 1/2 positive or 1/2 negative. Now, the way that these often show up on questions, here's a really typical way that I've seen this asked on exam. I mean, is a given combination of quantum numbers allowed? So I've shown different combinations. And when we say, is it allowed or not? We're saying, is it consistent with how the different values fit together? So what I'd like you to do is look at this closely right here. Let's answer it this way. Which ones do you find here are not allowed for some reason? Let me send you that as a polling question. So take your time, look at each of these. Look at each of the values as they're being listed. Think about what makes a quantum number allowed or not in relation to the other ones. And if it's not allowed, indicate that. Take your time on this one. I'm going to give you about 30 more seconds, and then I'm going to begin explaining how I'm looking at this. Okay, so share results with y'all. The consensus for the ones that seem like they might not be allowed, strongest consensus is with choices B and C. So let's look at B and C. So if I look within here for the relationships for B, it's saying that you can have a 3s orbital. Okay, I agree with that. You can have a 3s orbital, s because L equals 0, but then you can't have an m sub L value of -1, because if L equals 0, m sub L must also equal 0. So I agree with you. Choice B seems flawed for that reason. If I look at choice C, it's saying that you have a 2p orbital. I think you can have a 2p orbital. Could m sub L equal 0? Yes, it could be, because it goes 1, 0, and -1 are the three options. But that one runs afoul because you can't have the spin be equal to 0. The spin will either be +1/2 or -1/2. Either one is fine. You don't have to say it has to be one or the other. In fact, it has a different different meaning once you put it in a magnetic field. That's how it adopts a particular alignment. But my point here is, I think C is flawed because of the spin value. The other ones within the set, I think the other three are all right. I think that the first one here is representing a 3p orbital with an allowed m sub L value and allowed spin. I see a 3d orbital and a 1s orbital. Overall, I thought folks did a really good job with your first round for the analysis on that. This idea of thinking about whether it's allowed or not, which ones are in violation, really typical way that this gets asked. And to me, I come back to this representation right here. I find this to be a very helpful way to both represent and remember how the different quantum numbers are related. I know these relationships in the table, but for me personally, I find this visual a really helpful way to see what the allowed values are. Now, what I'd like to do is now spend some time when we've talked about the quantum numbers that correspond to different types of atomic orbitals. Let's see what they look like when we have different representations for them. When we want to look at this, we're going to represent them in a few different ways. Initially, I said they almost look like these cloud features. So what do we really mean by that? And we're going to see that we can represent them in a few different ways. One way is we're going to use what are called electron density and contour models. And then a different type of representation, which is called a radial probability function. So let's spend a little bit of time understanding these. So here, first of all, I show in the image here, different atomic orbitals. I've grouped these based on the different L values. And so notice that this matches up for the number of potential orbitals you have based on their m sub L values. When L equals 0, m sub L would equal to 0. When L equals 1, you had 3 options. L equals 2, you have 5 options. L equals 3, you got 7 options. So we're going to see next class how this fits with what we have then on the periodic table. But notice in this one, we have 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. That's what I mean when all the parts are fitting together. Let's start with the s orbitals here. So here I show 2 different ways that we can look at it. So first of all, this electron density one. This would be in the center of that axis there is where the nucleus is. And each of those dots is, if you were to take a picture and say, where is the electron found? Now where is it? Now where is it? If you were to take many, many different pictures, most of the time it would be found near the center. Less likely further away. And that's what we mean when we talk about the probability. It's not being found in a ring. It's being found in one region of space, and then another, and then another. Now, instead of always drawing those dots, these contour models, which look like spheres, those are simply being drawn to encompass, like usually it's like 90% of the time where the dots would be found. So instead of drawing all those dots again and again, they just draw spheres to represent that general shape. That's what a contour model is showing. And we're seeing that the spheres get bigger as I go from n equals 1 to n equals 2 to n equals 3. So s orbitals are spherical. Now, look, they're sort of like a baseball, let's say. They're a sphere of some kind. This was our electron density depiction and our contour model. Another one that's important for us here is what's called the radial probability. So let me connect this to the other one. So up here, this is as if we've taken our sphere and we've sort of sliced it, okay? So like we've taken an apple and we've just cut off an edge of it. What the radial probability is, it allows me to sort of look inside that sphere and consider what the structure looks like. It's as if you've taken an apple and you're looking from the seeds in the center out towards the edge. On the left-hand side, this is where the nucleus is. It's like the center of your apple. And you're asking, where is the electron found as I move further away from the center? So we see when it is a 1s orbital, most of the time it's close to the center, the most probable location. Notice what happens when I have a 2s. It could be near the center, but most of the time it's in this region a little bit further away. That's what they're trying to show in this color coding. It could be in the near the center or in this other region further away. It's interesting that there's this spot right here where it can't be at all. It could be in the center, it could be further away, but it's never at that spot in between. That spot right there where it goes down to 0 is what's called a node. I want us to understand that term. A node, N-O-D-E. This is a radial node. Now, this idea of having nodes, it comes back to describing the electrons as having a wave-like behavior. If you take a string and you have it vibrate, it can go up and down, up and down, up and down. If you take it and have it so that it's vibrating at a higher frequency, you can make what's called a standing wave. You can make it as if the wave appears to be stationary because it's going up and down, but in the center there, it appears as if it's just not moving at all. Or an even higher frequency, you can make it so it appears you've got 2 stationary spots. I don't know if you've ever seen this in a physics class or tried it, but if you take a string and you connect it to the wall and you just vibrate it, if you wave it up and down, or you shake it on the floor, if you get the frequency right, it has sort of like the snake pattern, and then it appears as if it's just sort of being stationary there, where you have spots as if it's not moving. Those are nodes. And so we see that within this model here, within our Schrodinger's model, we said that it has both a particle and a wave description. This aspect of including nodes, that's part of the wave description. If we have n equals 3, you notice we have 2 different radial nodes. Here's another close-up view on the nodes here for our s orbitals. When we have a 1s orbital, we don't have any radial nodes. A 2s orbital has a radial node. A 3s orbital has 2 radial nodes, and it keeps going up from there. So when I say note how the number of radial nodes increases, what I'm saying is the first time you have a type of orbital, the first time you have an s orbital, you don't have any radial nodes present. The second time you have it, meaning a 2s, now you have a radial node. A 3s, now you have 2 radial nodes, and they go right up from there. That's describing the structure that we have sort of inside the atomic orbital. So for a 1s orbital, I'd say the most probable distance that electrons found is about, what would you say, about half an angstrom away from the nucleus. What about the 2s? Take a second. What do you think the most probable distance it would be for a 2s orbital? If I look at that, maybe, what would you say? Maybe around 3 angstroms away from the nucleus? It might be, if you were to take a picture of it, it might be at 3, it might be at 4, might be at 2, might be at 6, might be at 0.5. might be back to 5, might be back to 3, might be back to 2, might be back to 3.5, might be back to 0.3. Notice how it's going to be found in one region or the other. And in a remarkable way, it's never going to be found at the node. Somehow it can go from this inner region to the outer region and never be found in between. And if we say, well, that seems crazy, well, let's think back to our Bohr model. The Bohr model said the electron could be at n equals 1 or n equals 2, but never in between. Same thing here. We've got particular regions where it cannot be found, and those are called these radio nodes. So if I look at this, then I try to think where it is on the energy diagram. I could think about a 1s as a contour. This would be its radio probability. That would be the ground state. A 2s, this would be its radio probability. It's found up here at n equals 2. And then I have a 3s. So notice how the first time, once again, that I have an s orbital, there is no radio node. The 2s has 1, the 3s has 2, and it goes right up from there. Here are the p orbitals. So within our p orbital, they're no longer spherical. We see that these are putting electron density above or below or somehow away from that nucleus. It could be above and below. It could be front to back. It could be left to right. We've got 3 different axes, x, y, and z. So it's arbitrary how we're choosing those. But a p orbital, it's putting electron density not at the nucleus. It's not a spherical one, but off of it. Now, the same electron, when it is in a particular orbital, let's say the pz, it might be found in this bottom lobe, and then the top lobe, and then the top, and then the bottom, and it's going back and forth. It's never being found in the center. But again, if we think about it as a wave, we're not going to stress about that. We're just going to say that the probability of where it's going to be found is in these 2 regions. So we see here sort of like the dot description and then the contour descriptions. So with a p orbital, that's L equals 1. So we have 3 different options, 3 different orientations in space, 3 different m sub L values. Here I show a radio probability distribution function for a p orbital. Take a second. What do you think the n value is for that p orbital? So I'm telling you that this is the radio probability for a p orbital. What do you think the n value could be? So as you're voting on that one, as you're polling on that one, let me talk through what I'm seeing within this. So as I'm looking within this one, I'm seeing that I have this most probable region where the electron would be found. The reason that this one right here, it's similar to the other radio probability ones, where on the far left-hand side, that would be considered the nucleus. And as I move away from the center, it becomes more probable where I would find it. So if it helps within your visualization, let's say that this is aligned along this particular y-axis. So at the nucleus right here, right at the center, which is on the leftmost side, there's no probability of finding it. As I'm moving further away from that, the probability increases. Now, I don't see any radio nodes present. I don't see, if I double back for what a radio node looks like, Remember, a radio node gave us like a bump in two different regions. I don't see that taking place at all here. I don't see any spot where it goes up and then back down to 0 and then back up again. So I would be interpreting this as something that does not have any radio nodes. And then the last feature is I do not have any radio nodes the first time I have that type of orbital. So I think this is a 2p orbital. I think n equals 2. And you might say, well, couldn't I make it n equals 1? You could, but there is no n equals 1 p orbital. The first time we have a p orbital is a 2p orbital. So my interpreting of this is, if you tell me this is a p orbital and there are no radio nodes present, it must be the first time I have that, and that's corresponding to a 2p orbital. This idea on the radio nodes part, the reason it's important, why am I spending some time with it, is because we're going to find that what's important oftentimes is the structure inside this orbital. It's not simply the shape. Is it pointed up, down, left, or right? It's the structure inside of it. So that's why these radio probability functions are important, because they tell us something about the probability, the location inside of the orbital. It's allowing us to look inside of this. Here's the d orbitals. We have 5 different d orbitals. L equals 2, so we have values ranging from -2 all the way to +2. Different m sub l values, they're not attached to particular orientations. I don't say this one has a value of -2 or this one has a value of 0. I just know that these must have different m sub l values, and that's what's giving rise to the 5 different orientations. 4 of them are really very similar. They're just aligned along different aspects of the X, Y, or Z axis. And then there's this last one, which is sort of goofy, which is looks a little bit more like a p orbital with this dumbbell around it, this donut around it. The d orbitals, we use those many times when we're looking in 1220 at aspects of different metals. I include here just the f orbitals. The f orbitals get even more funky, okay? I never use f orbitals. They're occupied by some parts of the periodic table, but I'm including these. These are not ones that you would need to memorize or try to match up. But let me ask it this way. Look at this one right here. What quantum number must be different for this one compared to the others? So these are all f orbitals. What quantum number must be different for that one compared to the other one? Let me send you a question on that. I'm really asking is, when we have these different options, they're different options because of which quantum number? Is it the n value, the L, the m sub L, or the m sub S? This particular one, the reason I'm asking it this way, I've seen this as a format for exam questions. As this one comes in, my dog over here is making me laugh. I guess I walked him too much. He's sitting on this futon, snoring away. I'm gonna have to share a picture of him next time. Rufus is the dog. Okay, so within this one, let me end the poll for you. Most folks are voting, about half of folks is saying they have different m sub L values. If I were to talk through the different choices, I think they all have the same L value because that's what makes them f orbitals after all. Remember, we said L equals 0 was an S, L equals 1 was a P. The L value tells me what type of orbital it is, S, P, D, or F. So if these are all f orbitals, they must all have the same L value. If they all have the same size as they're being represented here, I think they all have the same n value. What makes one different from the other, it is indeed the m sub L values. It's giving it a different orientation in space. Now, I mentioned this as far as being sort of a representative or what you might see on an exam. When I looked at the end of the chapter, the second part of the class that we were talking about, I think it's all been right here in this set of learning objectives. Relate the quantum numbers to the number and type of orbitals and recognize the different shapes. And interpret the radio probability functions. Both of those, that's exactly what we were spending time with at the end, where I was looking at representations. The kinds of things that I then see end of chapter. Here's two sets of examples. People have some good questions within perusal about, well, are we going to have to be able to draw atomic orbitals? I wish we could, but given the format for our exam, we can't have you draw them, right? We can't have you make a picture and somehow submit it. So these are two questions where instead of drawing it, you're interpreting it in different ways. You're interpreting them in terms of possible quantum number values. How would it be different if one of the quantum numbers change? So both of these, I think these are really representative of how you can get a picture of an atomic orbital and then turn it into different multiple choice questions. So both of these, 6.9, 6.10, these would be ones that you probably want to check, because I think that they're beginning to say, how can we have questions about atomic orbitals and connect it to different features? These ones on the left-hand side, this first one comes back to the relationship for what quantum numbers are allowed. If n equals 4, what would be possible L values? If L equals 2, possible M sub L values. So this is looking at relationships among allowed quantum numbers. 6.62, same thing. This is one that I included within the pre-class video. This last one, 6.64, asks you to sketch the shape and orientation. You're not going to have to sketch that, but we want to have that understanding. So what I would ask you to do as a learner within that, ask yourself, okay, let me see if I can answer that. But then let me also challenge myself and think, okay, how would this now appear as a multiple choice question? Would it give me the image and ask about the different options? Would it somehow change it? That's what I would say, that's what's matching our objective. And then this last one here, 6.54, this is one where it's now bringing once again back to the idea of a radio probability function. It's asking, how do we interpret it? What are the different regions telling us? Stuff like that. I know that within the practice test, you're going to find questions on all of these ending topics. You're going to find questions about radio probability distribution functions, atomic orbitals, and quantum numbers. And with that, folks, I'll hang around for questions. You did an outstanding job tonight. If you got questions, I'll be happy to host them.
Hey, Dr. Clark, I had one question about the diagrams from earlier relating the number of nodes.
Yeah.
And I think it was energy levels, principal quantum numbers.
Like this guy?
Yes. So is the relationship the number of energy levels is also the number of nodes?
I think it actually, hold on one second. Jacob, if you're hanging around, I'm going to, for the review one, I'm going to switch the deadline. I'm going to move it ahead to make it on Thursday. I think the actual one, as you put it together, I think that the number of nodes is n minus L minus 1.
Minus L minus 1.
I think so. Let's see if it works. So n minus L minus 1. If I have a n equals 1, L equals 0, 1 minus 0 minus 1 would say no nodes here. This would be 2 minus 0 minus 1. That gives me 1 node. 3, you know, so it's working for those. If I think over here with the 2p, this would be 2 minus 1 minus 1. Yeah, it gets down to 0. So I think that is the actual If you want to turn it into expression, the radio nodes would be n minus L minus 1.
Gotcha. Okay, thank you.
Yep.
I have a question.
Mhm.
What, like when the photons of light hit the metal, what's like released? Is that electrons or is that photons released from
Yeah.
the metal?
Real good question. So within the photoelectric effect, those are electrons that are leaving the metal surface. So it's enough energy to cause the electron to be ejected, removed away from the metal entirely.
Okay, so then I'm confused how that relates to like 6.5, because like when you're like, so a photon's emitted when an electron falls down or something
Oh,
like
okay.
that?
Really good question. Let me double back for you. So initial thought, when we talk about photons, a photon, I mean, in a way, it sort of depends. How literal do we want to say a photon is a particle? A photon we can think of as the smallest amount of energy that we can have. In a way, it's like a particle of energy, but it's still like an amount of energy, okay? And so if I'm looking at a case within the photoelectric effect, I'm saying that I'm directing energy at the surface. Sorry about that. I'm directing energy at the surface and it's causing electrons to be ejected. That would be in the photoelectric effect. If I'm looking at it in the Bohr model, it's again, I mean, we sort of have to think about it as sort of particles of energy, if you want to think about it that way. So when we look at then what takes place with the within the simulation here, we're going to be sending in photons, which are different particles of light. When those particles of light interact with the electron, it moves it from one location to another. It moves it from one energy level to another. That energy, when it comes in, let's say it moves it from n equals 1 to n equals 5. A photon energy comes in and moves it from 1 to 5. Once it's at 5, it could come back down by going 5 to 1, or it could go 5 to 4 and then 4 to 1, or 5 to 4, 4 to 3, 4 to 3, 2 to 1. It could come down in stages. The total energy ends up being the same, but whether you get one photon coming in and the same number going out, you can get more photons going out than you got going in. They add up to the same amount of energy, but they don't have to be, the number of photons isn't conserved, it's the total energy is. So when we're looking then back within this expression, this question, see if I'm getting to it. We're then saying that we had a electron get excited to a higher state. Now, when it goes from a higher to a lower one, energy is going to be emitted. That energy is going to take the form of a photon. So I'm looking for one where I'm starting out from a higher energy level going down to a lower one. If I were to think this back to the photoelectric effect that you had, in a way, when we're looking at the hydrogen atom, these electrons are taking place between these different energy levels. If you add enough energy, though, to make it so it goes all the way up to here to infinity, n equals infinity, what you've done is you've completely removed the electron. You've completely ionized it. You've completely removed it from the atom. In a sense, that's what was happening with the photoelectric effect. You had a photon coming in, and it wasn't moving it just to an excited state. It was entirely removing it from the metal. When we're looking at that simulation, we're moving it to excited state, but we're not entirely removing it. We're going to look to see what happens if you entirely remove it. That's what we're going to look at in next chapter. But in this one, it's all still staying within the atom.
I see. So can you like can the electron, like when it falls, it doesn't only release visible light, right? It can also release like X-rays or
Absolutely.
like that.
Yeah. And in fact, if we look at if I get back to this image, If it's in the ground state here, if it's at n equals 1, the only way we end up seeing visible light is I've got to have ultraviolet or something strong come in to move it up high enough so I see it when it falls back down here to n equals 2. So you're absolutely right. It can come in, it can get excited, and then on the way back down, maybe on the way back down, it gives you some infrared and then some visible and then ultraviolet. It could give you all of those different ones on the way back down.
Cool. Thank you. That
Yep.
makes sense.
I just had a question real quick about the extra credit and everything.
Mhm.
When we have those extra credit assignments on perusal, there's not anything extra specifically that we have to do with it. Is it just like us just trying to fill the normal 6 to,
Yeah.
I mean, 4 to 6 comments and everything?
Yep. Just engage with it like usual. And what I'm going to do is you don't have to do anything better, different. Just see if it's helpful for you. And I think it will be. What I'm finding, the kinds of questions people are leaving within that, it's a combination of, hey, I don't know how to do this, but then also good questions about, well, are we going to have to do this and this? You know, sort of like procedural ones or logistic ones. So I think those are good things that you can add too. Just try it and see if it's helpful for you. And then I'm just going to take points within that, and I'm just going to add it to people's total within perusal. I'm calling it extra credit, and this might be, I might be doing you a disservice. At the end, everybody does fine in perusal. Okay, so don't feel like you need to scramble if it's not helpful for you. Spend your time elsewhere, but I think it will be helpful.
Okay, thank you. You have a good night then.
Thanks.
I had a question about the perusal assignment today.
Mhm.
In there was a question about L equaling -1, and I didn't quite understand that.
Yeah, I think I'd have to look back because I'm not sure exactly if we're looking at the same thing. I would say that my L value, the smallest I can have for my L value, it should be 0. I think my M sub L values could then go from -L to +L, but L itself, I think the smallest it can get is going to be a 0. If I had something in there where it suggested the L itself could be negative, that's not going to be a allowed value for it.
Okay, I might have misread it then. I just know it gave us answers, and none of the answers really made sense. It was like 1, 2, 3, and then 1, 2, 3, 4. Then there was like a negative something all the way up until a positive. If that makes any sense.
Yeah, I don't remember the format from that. I think that was one that I grabbed that was like within the e-text within that. But I would say within that, if the stuff that we were discussing tonight as a framework was making sense to you, don't feel like that was any special or anything tricky or anything like that. I wouldn't go back to try to decode that one.
Okay, that works. But thank you. I appreciate it.
Sure.
Have a good.
I have a quick question. So, like, I learned about electron configuration in high school chemistry.
Mhm.
How does this relate to that? Because I recognize seeing like 2s, 2p, and then 3s, 3p, and then I just remember it was like 4s and then 3d and
Yeah.
then 4p. And it's like it's a little different than what we're learning right now, but it's like the same concept. So I'm like, I don't know if I should connect those two or like, I don't know.
Yeah, no, that's great. You're what you're describing within that is exactly where we're going to go next class. So within let me find my image. It's exactly where we're going. I would say within this one, we've looked at the different atomic orbitals for the hydrogen atom, and we've added this designation for them. Whether we're talking about an s orbital, a p orbital. So we've come up with that designation, but right now we've only been looking at the hydrogen atom, so we've only had one electron that we were interested in. What you're describing right there is, for an electron configuration, is Well, what happens as soon as we have more than like one electron? Where do we begin to put them? And what are the, what's sort of the order for that? And that's exactly what we're going to do next. We're going to connect these atomic orbitals with then how we fill them up and how the periodic table fits together with that.
Okay, so if hydrogen only has one electron, shouldn't it just be 1s? Why are we like talking about n equals 2 and then n equals 3?
I love it. Great question. Now, let me ask you this. When we looked at the Bohr model a little bit earlier, and we saw that the electron could be on different rings, it started out on that inner one, right? N equals 1. Did you get upset when it moved out to, let's say, n equals 3 or n equals 4? Could it move out to those other rings?
Yes, because I mean it's still one electron. But
Yeah, okay. And the reason I ask is within this one, it can be at n equals 1 at the bottom one, but when it moves out to these other ones, it's as if it's moving out to another ring. It's just moving further away. In that Bohr model, we had the inner ring and then other ones that it could potentially move to. It's still only one electron. The ground state is still when it's in that n equals 1, but we had other rings it could potentially move to. In this case, we have other atomic orbitals it can move to. You're absolutely right that the lowest energy, the ground state, would be when it's in the 1s. But we've got all these other options where it could be too. So just like in the Bohr model, we had excited states where we can move it further away. Same thing here. We can move it further away and call those excited states too.
Oh, okay. That makes so much more sense because I was trying to understand this like entire concept, but I kept mixing it in with the electron configuration. And even though it is the same thing, there were like just so many questions I had about it.
Well, what you just, in the way that you said it right there, I hear that so many times where people are okay with the Bohr with these different rings. But then I think in high school, you work so hard to come up with the electron configuration order. And then when you start to see these other ones, it's like, well, why do I need that? I already know what the electron configuration is. The electron configuration is telling you the ground state, but you still have all these other options where it could be too.
Okay, that makes more sense because like I just remember every time I see those squares, I fill them up with two arrows, one going upwards and one going downwards. Like, you know what I'm talking about? So
Yeah,
like,
no, I absolutely. And and in a way, if you have some skill with that, don't say that that is completely irrelevant. But let's see, we're going to add up a little bit more to try to figure out what you are actually doing. Because I know in high school, a lot of times it's, well, here's these boxes, let's fill them up this way. It's a lot of pattern recognition without even knowing what you're doing. Because I noticed within perusal, a lot of people have questions about, okay, I heard about a 1s orbital, but I never knew that this is the framework where it came from. So we're just trying to expand a little bit to know more where the task that you were doing actually fits with what was going on.
okay, that makes more sense. Thank you. Also, what can I do to like understand the relationship between L and then M's of L? I'm not sure if I'm like
Yeah. I think the way that I make this kind of image right here, I think this, what I got on the screen right now, to me, this summarizes all of those features. Because at the bottom part right here, this shows what the rules are. How n starts at 1 and goes up from there. 1, 2, 3, 4. L then goes from 0 all the way to n minus 1. M sub L then goes from positive L all the way to minus L. So that's showing the relationship amongst where they fit together. And then in this picture right here, these are also illustrating that same one, because you notice you can have n equals 1, 2, 3, goes up from there. The possible L values that you have, I'm grouping those as well. You can have L equals 0, L equals 1, L equals 2, but in each of these cases, it's always at n minus 1. So this fits together with the same pattern right here. So some people like to sort of remember what these relationships are, the rules, if you will. I like also having this picture because this is summarizing right there what the allowed quantum numbers are. So if the question is, can you have n equals 2 and m sub l equals 2? Well, if I look at n equals 2, no, I can't have m sub l equals 2 because I don't have that until I equal this next one right here. So my point is that these relationships, these are sort of like the rules for how they fit together, but then they lead to this picture that I'm trying to show with the other atomic orbitals.
Okay, that makes more sense. Okay, yeah, I was just having a, I don't know, hard time like reading how the information was organized, but like all the P's are L equals 1, all the D's are L equals 2. Okay, that makes
Yep.
much more sense. Thank you so much.
Yep, you got it.